Hello everyone. Today's topic, antiderivatives. We have two objectives. We want to introduce antiderivatives of a function. Also, we want to show some examples of antiderivatives. We start with the main question. Why do we need antiderivatives? A quick answer. For instance, a physicist who knows the velocity of a particle might wish to know its position at a given time. A function f is called an antiderivative of a function lowercase f on some interval I if the derivative of uppercase f is the lowercase antiderivative f of x for all values of x inside of that interval I. If function f is an antiderivative on some interval I, then the most general antiderivative of f will be f of x plus c, where c is called a constanta or is an arbitrary constant. So why don't we take a look at a specific example? The derivative of the function f of x is x. The most general antiderivative is f of x equals to x squared over 2 plus some constanta c. We want to verify the answer by differentiation, so f of x by definition, it's f prime of x, which is the same as to write ddx of x squared over 2 plus some constanta c. It's 1/2 derivative of x squared plus 0, since the derivative of any constant is 0, which equals to 1/2 x to the power of 2 minus 1 times 2, or will give us the original derivative function f of x equals to x, check mark. And certainly the constanta c can be any number. C sub 1 equals to 0. That's the blue curve. When constanta c equals to positive 2, that's your orange curve. When constanta c, let's say c sub 3 equals to minus 2, you can see it from the graph. You have a black parabola. And all of those parabolas do represent particular solutions to the given example. Again, how many solutions are there? The answer will be infinite many. I would like to move on. Here is the table of anti-differentiation formulas. Let me zoom in on it. So if the original function is a polynomial, then the particular antiderivative will be computed using the power rule formula. If the original function is an exponential, then the same function will be antiderivative. For a cosine function, for instance, antiderivative will be sine, and for the sine function, antiderivative will be minus cosine. Again, I suggest to go over this table and certainly practice finding antiderivatives of a function. I'm going to show an example. We need to find the derivative f of x if the second derivative is given by the following equation. So the first step, we want to find the first derivative, f prime of x. F prime of x will be equal to antiderivative, this is the integral sign of the given function dx, or antiderivative of 6x squared minus 6x plus 4 dx. And we need to locate the appropriate formula. We're going to use the power rule. We'll have 6x squared plus 1 over 2 plus 1 minus 6x to the power of 1 plus 1 over 1 plus 1 plus 4x plus some constanta c if we simplify, we'll have 6x cubed over 3 minus 6x squared over 2 plus 4x plus some constanta c. And if we simplify one more time, that will give us 2x cubed minus 3x squared minus 4x plus constanta c. We can take the c value to be equal to 0, for instance. And then the original function f of x will be antiderivative of f prime of x, or antiderivative of 2x cubed minus 3x squared minus 4x dx, which will give us 2x to the fourth power. Let me do it step by step. 2x to the power of 3 plus 1 over 3 plus 1 minus 3x to the power of 2 plus 1 over 2 plus 1 minus 4x to the power of 1 plus 1 over 1 plus 1 plus another constanta d, and that will give us 2x to the fourth over 4, or x to the fourth over 2 minus 3x cubed over 3 or minus x cubed minus 2x squared plus some constanta d. Now we can easily confirm the results by differentiation. So if f of x, I rewrite the result, equals to x to the fourth over 2 minus x cubed minus 2x squared plus d, then the first derivative, f prime of x, will be 4x cubed over 2 minus 3x squared minus 4x plus 0, or f prime of x will be equal to 2x squared minus 2x cubed minus 3x squared minus 4x. And then the second derivative will be equal to 4x minus squared minus 6x minus 4. And we're back. Three times 2, 6. Sorry about that. Let me correct myself. 6x squared minus 6x. This is the plus. This is the plus. Plus 4. And we're back to the original function. You can see the graph of each one. The red, that's the second derivative. Green is the first derivative. And blue, or perhaps I should say pink, is the function f of x. Moving on. Next example. Again, we do have the first derivative. Let me rewrite it. F prime of x one more time is 2 over x squared plus 3x to the power of minus 3, which we rewrite as 2x to the power of minus 2 plus 3x to the power of minus 3. And we need to find f of x. What is f of x? Its antiderivative, f prime of x, or antiderivative 2x to the power of minus 2 plus 3x to the power of minus 3 dx, which will give me 2 times x using the power rule, minus 2 plus 1 over minus 2 plus 1 plus 3 times x to the power of minus 3 plus 1 over minus 3 plus 1 plus some constanta d. If we simplify, that will give us 2x to the power of minus 1 over minus 1 plus 3x to the power of minus 2 over minus 2 plus some constanta c. Another example. Again, we have a function f prime of x equals to 2 sine x. The red curve. Function f of x antiderivative, or 2 sine x dx. That will give us minus 2 cosine x plus some constanta c. Blue curve is your antiderivative. And we can confirm the result by verifying. Just simply find the derivative of f of x. Again, f of x, let me rewrite one more time. It's minus 2 cosine x plus constanta c. F prime of x, if we take the derivative, will give us derivative of minus 2 cosine x plus 0, or it is the same as minus 2. The derivative of cosine is minus sine x, which will give us 2 sine x, check mark. We're back to the original function. I would like to show one more example how to find antiderivative. Suppose a particle is moving with the velocity, let me rewrite one more time, v of t equals to sine t minus cosine t. V of t, red curve. Given the initial position s of 0 equals to 0, we need to find the position of the particle. Well, s of t will be equal to integral or antiderivative of the velocity function, or sine t minus cosine t dt. And if we use the table, the antiderivative of sine t will be minus cosine t. Antiderivative of cosine t will be sine t plus some constanta c. And that will be the position function. S of t equals to, I will rewrite one more time, minus cosine t minus sine t plus some constanta. To confirm the result, that's the position function S of t blue. To confirm the result, we are going to verify the first derivative of the position function is the velocity. If we do it step by step, ddt of minus cosine t plus ddt of minus sine t plus 0 will give us the derivative of cosine is minus sine, so it will be minus of minus sine t. The derivative of sine t cosine, so minus cosine t. And if I rewrite one more time, minus and minus will give me a plus sine t minus cosine t, and that is exactly the velocity function, check mark. A quick summary: we have introduced antiderivatives of the original function. You should be able to find those antiderivatives using the table, using the appropriate formulas, solve the initial value problem, and be able to recognize each function from the graph or graph the derivative and antiderivative as the functions. And that concludes today's lecture.